तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Last class we were discussing about activated sludge process, that is a secondary treatment process. So, in activated sludge process we have seen what is happening. The wastewater is coming to the aeration tank, there we are supplying enough air and nutrients and other requirements for the microorganisms are already present along with the wastewater. So, what happens when we supply enough oxygen, the microorganisms will be oxidizing the organic matter into carbon dioxide and water, and as a result new cells will be generated. And in the aeration tank what is happening, the organic matter which is in dissolved form is getting converted into microorganisms or in the colloidal form. So, we have to separate this microorganism, that is why secondary sedimentation tank is an essential part of activated sludge process. And we have also discussed the kinetics of activated sludge process. So, how can we find out the microbial concentration in the aeration tank? How can we find out the substrate concentration or the BOD, whatever is coming out of the secondary sedimentation tank? And we have also seen that how can we find out an expression for the recirculation ratio, because these are the important parameters whenever we talk about the design of an activated sludge process, because most of the time we design the activated sludge process based upon the biokinetic parameters. And we have also discussed about two different terms. One is hydraulic retention time and another one is biological sludge retention time. Whenever we talk about any biological systems, the BSRT or the biological sludge retention time is very important. This is nothing but the time at which the microorganisms are staying in the system, and if they stay more time in the system, naturally the amount of microorganism in the system will be more depending upon the supply of substrate. So, these are the important parameters. Then we were discussing about sludge volume index. This is a number which shows the settling characteristics of the sludge in the secondary sedimentation tank, and sludge volume index is very important as far as the performance of the activated sludge process is concerned. Why it is so important, we will see. Okay. So, we have seen that if sludge volume index, that means the volume occupied by unit mass of sludge. If sludge volume index is less than 100, it is a good sludge, and if it is 100, it is desirable, and if it is 150 or above, it is a bulking sludge, and if it is above 200, it is not at all desirable, or we have to change the system. So, why it is so important, or how it is controlling the performance of the activated sludge process? Because what is happening, we are recirculating the sludge to the aeration tank. The purpose of this recirculation is nothing but improving the concentration of microorganism present in the aeration tank. If your sludge is bulking, then what will happen? Recirculation we are controlling based upon the volume. So, if the concentration of the sludge or the volume occupied by the sludge for a unit mass is high, then what will happen? Though we are keeping the recirculation ratio as a constant, the amount of microorganism whatever is going to the aeration tank will be getting reduced. As the microbial concentration get reduced in the aeration tank, definitely the performance of the system will be decreasing, because here in activated sludge process or in any biological system, the workers are the microorganism. So, if you reduce the number of workers, definitely the amount of work done by them will be getting reduced. So, that is the reason why high SVI is not preferred in activated sludge process. And I have already explained how to find out the sludge volume index. We usually use a 1 liter graduated cylinder, and we have to take well mixed 1 liter of mixed liquid suspended solids and allow them to settle for 30 minutes of settling, and find out what is the volume occupied by the sludge in the graduated cylinder. So this will be obtained in terms of ml. Then what we have to do is find out the concentration of the MLSs by filtering and taking the tri weight. So we will be knowing what is the volume occupied and what is the weight of the MLSs. So from that one we can find out what is the volume occupied by unit mass of sludge. So this is SVI, the unit is in milliliters per gram, that means liters by 10 raised to 6 milligrams. So this is the thing. And XR is nothing but the concentration of biomass present in the recirculated sludge, that is nothing but 10 raised to 6 by SVI, because SVI unit is liters per milligram and XR unit is milligrams per liter. So this is very, very important, and this XR is the one which decides the effectiveness of the aeration unit, because as we recirculate, okay, if the XR value is more, okay, and if you fix up your recirculation ratio, say 0.25, then what will happen in that 0.25, so much of biomass will be present, so the total biomass concentration in the aeration tank will be increasing. So in most of the cases, this SVI is used for proper operation of the plant. Based upon the SVI, we can calculate XR, and this XR and the biomass concentration in the aeration tank can be adjusted using proper valves. So this SVI is very, very important. Now we will see, we have seen how to find out the concentration of biomass in the activated sludge. Okay, we got some expression in terms of the biokinetic parameter, and we have seen what is the SE value we can get in terms of the biokinetic parameters like YT, KD, theta C, etc. And we have also seen some expression for recirculation ratio based upon the biokinetic parameters. So these expressions are available. So how can we design an activated sludge process? There are 3 different design problems one can face. Okay, one is the biokinetic parameters are known and the required treatment efficiency is given. Okay, you have already found out the biokinetic parameters of the system and efficiency, because you know this is the effluent discharge standard. So we can find out what is the efficiency required. That means you know the initial BOD and you know what should be the final BOD. So you know what is the treatment efficiency required. So how can we design the system? So this expression we have already seen. Okay, theta C equal to this expression, or the expression we can change in the other way, VA, that means volume of the aeration tank into concentration of the biomass is equal to theta C, this is biological sludge retention time, into flow rate into yield coefficient into initial BOD minus final BOD divided by 1 plus this is the decay constant and this is the BSRT again. So SVI is given, this is equation is there, and the other expression we have is 1 by theta C is equal to Q by VA into 1 plus R minus R into XR by X. Okay, these equations we have derived in the last class. So from equation 1 and 2, what we can do is we can find out X and VA. Okay, here we will be knowing theta C, we know Q, we know YT, we know KD, we know S naught, we know SE. The only unknown is VA and X. And here also we know Q, theta C, and R we know it is in between 2.5 and 0.25 and 0.3 ratio. And XR we can find out from the SVI, because SVI we will be knowing. So only 2 unknowns are VA and X, and we have 2 equations. So we can find out what is the X and VA value. Okay, but we know that the recirculation ratio can be changed from 25 to 30%. So by changing, putting different R value, we will be getting a series of curves. From that one we can find out what is the optimum value. So this is one way of designing activated sludge process. We will see what is the second type of problem. Here X desired is known. Okay, so it is given that this much of biomass is present in the system and SVI is known, sludge volume index is known, and SE is defined because that is the effluent discharge standard. So, we can find out what is this K. K is nothing but Q max, this is maximum specific substrate utilization rate divided by Ks, this is the half saturation constant. Okay, so, K is known and you know Q is specific substrate utilization rate is nothing but K into SC and that is equal to Q into S0 minus SC. This is the total substrate coming to the system and this is the total biomass present in the system. So, this equation is known. So, VA can be calculated. What is the volume of the aeration tank required? This is the same thing we have to calculate. So, we will be able to get this one. And we have another equation 1 by theta C, okay, that is the minimum biological sludge retention time whatever we have to provide, that is equal to mu, which is equal to YTQ minus KD. These expressions we have seen already, how we are getting these expressions. So, if you know this one and we know what is theta C, theta C is nothing but, okay, how much time the sludge is remaining in the aeration tank, that is nothing but the total sludge or total biomass present in the aeration tank divided by how the sludge is getting removed from the system. So, from that expression we can calculate what is the sludge wastage required, and if the sludge wastage is known and SVI is known, we can find out what is the recirculation ratio required. So, here X is given, so we are calculating VA and we are calculating again QW, what is the sludge wastage, and we are also calculating R based upon the 3 equations whatever we have derived earlier. Now, we will see what is the third problem. Third problem is theta C is not known. So, we have the biokinetic parameters. So, we know that what is this theta C? Theta C is nothing but 1 by mu or 1 by specific growth rate, and mu value is changing for a system, but the mu max, the maximum specific substrate utilization rate is a constant, and if you take 1 by mu max, we will be getting what is the theta C minimum required, because as the mu max increases, theta C value will be decreasing. So, since we know the mu max value, we can find out what is the theta C minimum we have to provide. So, assume a theta C value which is greater than this theta C minimum, which is equal to 1 by mu max, and then we can use this expression 1 by theta C minimum is equal to YT Q max S naught by Ks plus S naught minus Kd. Here what is happening is when theta C is equal to theta C minimum, okay, up to that stage no substrate removal is taking place, and once the theta C is greater than theta C minimum, then only the substrate removal will be taking place. So, that is why we are putting S naught here instead of SC. Okay. So, we can find out what is this theta C minimum, that is nothing but YT K into S naught. So, these are the 3 different problems or 3 different ways how we can design an activated sludge process. Now, we will see, okay, till now we were discussing about the conventional activated sludge process, but the conventional activated sludge process is having some problems. So, there are various process modifications based upon the requirement and depending upon the nature of the wastewater and the quantity of wastewater coming to the treatment unit. So, based upon that one we can modify the conventional activated sludge process. So, we will see what are the modifications of the conventional activated sludge process. Okay. One is contact stabilization, another one is step aeration or tapered aeration system, fourth one is extended aeration system, and fifth one is high rate activated sludge process, and there is another one which is sludge reaeration. Okay, it is not a process modification. To improve the efficiency, in earlier days what people used to do is take the sludge, reaerate it before putting it back to the system, so that the oxygen deficiency will be less in the system. So, that is again another modification or another type of activated sludge process. Now, we will see one by one in detail, and when we have to go for these modifications or what type of wastewater, okay, we can go for conventional activated sludge process, and what type of wastewater or what quantity we can select one of these modifications. Okay, we will see in detail. So, this is the conventional activated sludge process. Till now we were discussing primary sedimentation tank, then aeration tank. Here we are having the sludge wastage WC, and this is the secondary sedimentation tank, and some excess sludge will be there, that will be going to the digester, and this is the recirculation system, and it is coming to the aeration tank. And in conventional activated sludge process, in aeration tank we give 6 to 8 hours of aeration, okay. And please remember, this is not a design parameter, okay. Design parameter is theta c and x and AC, we have seen that one, and recirculation ratio, but usually this is the time we usually give in the aeration tank. And in conventional process, an MLSS concentration of 2000 to 3000 milligram per liter is always maintained, and another term used in activated sludge process is MLVSS. MLSS is the total suspended solids present in the system. So we know that along with the wastewater, some inorganic solids also will come. So in MLSS, mixed liquid suspended solids, organic as well as inorganic solids will be coming, but we are interested only the microbial concentration, because whenever we talk about the sludge, we are interested only the microbial concentration, because those are the things which is affecting the performance. So how can we find out this one? So we usually use another term that is known as MLVSS, that means mixed liquid volatile suspended solids. So if it is volatile, that means it is organic in nature. So in the mixed liquid suspended solids, whatever is organic in nature or whatever we can volatilize, okay, that is mainly the sludge or the biomass. So many experiments were conducted in the lab and the field, and it is found that if you take a ratio of 80% or 0.8, then we can get the MLVSS, or the other ways MLVSS is nothing but 0.8 times MLSS. And recirculation ratio in conventional process varies from 0.25 to 0.33, sometimes it goes up to 0.5 also. Now we will see what is the limitation of this conventional system. Okay. So usually we give diffused aeration system or surface aeration system. So in diffused aeration system, what, okay, or in conventional activated sludge process, what we do is the oxygen supply is uniform throughout the aeration tank. That means from the inlet to outlet, the oxygen supply is uniform. But we see, if you see the oxygen requirement, so how it is varying. The oxygen requirement will be more in the inlet, because the wastewater with high BOD is coming into the inlet, and the recirculated sludge also will be coming to the inlet. So definitely the inlet, the oxygen requirement will be more, and as we pass through the aeration tank, okay, we are assuming that it is a plug for reactor, so now longitudinal mixing, so it is moving with respect to time. So as it moves towards the outlet, so what will happen, the BOD will be gradually decreasing, okay. So naturally the oxygen requirement of the system will be decreasing. So if you take the oxygen requirement or oxygen utilization profile in an activated sludge process, it will be coming something like this. So in conventional system, here oxygen deficiency will be experiencing, and here excess oxygen will be available. But if we can provide oxygen in this way, then the system will be having more efficiency. So that is what here, match the oxygen utilization profile, okay, then the system will be more effective. So that is what is done in step-fed system or tapered aeration system, okay. That is one modification of conventional activated sludge process. So in tapered aeration system or step-fed system, what happens, the wastewater whatever is to be treated in the aeration tank or the activated sludge process, it will not be entering in the same pot, okay. The wastewater will be distributed throughout the length of the activated sludge process. Here we can see it clearly. Q is coming and Q is divided in M, divided into M, and each Q by M is entering in different compartments, okay. This is the aeration tank. We are assuming that it is having M compartments, okay. There will not be any division like this, but we are assuming that, okay, this is divided into M different compartments. So Q by M is coming with an BOD of S1, and Q by M is coming to the second compartment also, third, and even in the M compartment. So if you see the BOD profile along with the length of the reactor, what will happen? Here you will be having S1, and as it moves from here to here, the degradation will be taking place and this will be reducing. Okay. Then again what will happen, we are adding fresh sewage here in the second compartment, so it will be slightly increasing and again decreasing. This point is lower than this point and this will be keep on happening. So why it is coming down drastically? Because the degradation will be taking place, along with that one dilution also will be taking place, because this liquid will be coming to this place. So dilution also will be taking place. So finally you will be getting the BOD of this much concentration. Okay. So if you go for conventional aeration tank or conventional activated sludge process, you will not be able to achieve this much of BOD reduction. So this type of system is suitable for high BOD wastewaters. Okay. For example, distillery wastewater, dairy and food processing industry wastewater. So there the oxygen requirement will be so high. So whatever aerators we are providing, they will not be able to supply that much of oxygen, whatever is required in the entrance of the system or the influent chamber of the system. So if you can divide the wastewater into different compartments, so what will happen, the high oxygen requirement will be equally distributed along the length of the aeration tank. So the efficiency will be much more. Okay. The advantages of this tapered aeration system or step-fed system is lower the peak oxygen demand, because we are distributing the flow, then better equalization of waste load within the aeration tank and better distribution of oxygen demand over the entire length of aeration tank, and smaller aeration tank volume compared to the conventional activated sludge unit, because here we have seen biodegradation as well as dilution will be taking place and the concentration gradient available, okay, high, then it will be reducing, then again it will be increasing and reducing. So you will be getting high and low concentration gradient, so that will be increasing the degradation efficiency, and moreover the volume of the waste present in the tank will be effective in the dilution. So because of these reasons, the volume required in tapered aeration system is less than the conventional aeration system. Now we will see what is this modification extended aeration system. Okay. Here what is happening is, okay, we have seen that in activated sludge process the biomass is present and the wastewater is coming with high organic matter and we are providing the aeration. So during aeration the organic matter is getting converted to carbon dioxide, water and fresh cells. But in extended aeration system what happens, the food supply will be limited and the aeration time will be comparatively larger. So what will happen, whatever the food is available, first it will be getting converted to biomass, and afterwards what will happen, there will not be any food available in the system. So whatever the biomass is present in the system, they will be undergoing auto-oxidation or endogenous respiration. Okay. Are you remembering the growth curve of microorganism? We have a lag phase, then a low growth phase, then stationary phase and endogenous respiration phase. In endogenous respiration phase what will happen, the microorganism, the cells will be utilized, some cells will be utilized by other microorganism as the food and energy sources, that is endogenous respiration. So in extended aeration system this endogenous respiration will be taking place, or external substrate is completely removed and auto-oxidation, or internal substrate is being used. So net growth in the system will be equal to 0. There will not be any excessive biomass production in the system. Or we can write like this, dx by dt growth. Okay, the biomass growth is equal to 0, or if you write the mass balance equation, dx by dt growth into Va. Okay, this is the total change in microbial concentration in the aeration tank, that is equal to ytq minus kd into x into total volume. Okay, and we have seen that the net growth is equal to 0, or from this equation we can write like this, yt into ds by dt is equal to kd into s. So this is the expression for extended aeration system, or we can write q is nothing but q max sc by ks plus sc, that is equal to kd into x, or q is equal to kd by yt. Okay. So this is the expression for extended aeration system, and Q is nothing but Q into S0 minus SC by VA. And in conventional activated sludge process or in extended aeration system, if you see Q is equal to, Q will be coming around 0.1, and in conventional activated sludge process Q is equal to K into SC, that is equal to around 3. And if Q, S0, SC and X are the same in conventional activated sludge process and extended aeration system, the volume required in extended aeration system is 30 times that of conventional activated sludge process, because here we have to give much more time for the auto oxidation of the cells, okay, because in conventional activated sludge process we will be keeping the system in the stationary growth phase, okay, but in extended aeration system we are aerating it for such a long time that all the external carbon source is completely utilized and internal carbon source will be utilized afterwards. And advantages of this system is sludge production is minimal, because whatever sludge, initially the sludge will be producing, but whatever the sludge produced, everything will be undergoing auto oxidation. So the net sludge production will be very minimal, and moreover whatever the sludge available, okay, or whatever the sludge present in the extended aeration system, that will be completely stabilized. So we can just discharge it and put it into the sludge trying buds, or we don't have to go for any sludge digesters, okay. So like that, sludge handling in the extended aeration system will be much easier, okay. So that those are the advantages of this system. One, the sludge production is minimal and the sludge is stabilized, no digesters are required, and nutrient requirement is minimal. Why it is happening? Because biomass will be produced and they will be auto oxidized. As a result, carbon dioxide and water will be formed, and the nutrients, the nitrogen, phosphorus, etc. will be still remaining in the system. So whenever new biomass is produced, that will be utilized, and again the same thing will be coming back to the system. So the nutrient requirement of extended aeration system is much lower compared to conventional activated sludge process. But obviously there are certain disadvantages of this system. One is high power requirement, because we have to go for aeration for such a long time. So definitely the power requirement is high, and large volume of aeration tank, because we have to keep the wastewater for such a long time and aerate it. So the volume of the aeration tank become very high, and this extended aeration system usually practiced for small communities where the wastewater quantity is less, and if they don't want to go for sludge digesters and all, okay, this is the best treatment option, and we can get 90 to 95% of BOD removal efficiency in this system, okay. And now we will see what is the biological sludge retention time in the extended aeration system, okay. Theoretically speaking, the BSRT is infinity, because we are not wasting any sludge from the system, okay. In conventional activated sludge process we are wasting the sludge, so we can find out what is the BSRT, that is nothing but the total sludge divided by whatever is the sludge wastage daily. But in conventional system, in extended aeration system, so this is the equation we have, mu, the specific growth rate is equal to YTQ minus KD, okay, and you know that mu is equal to 0 or theta c, okay, that is the BSRT. Theta c is nothing but 1 by mu, so it will come 1 by 0, okay, 1 by 0 is infinity. But practically, okay, we cannot provide infinite time in the aeration time. So usually we give a theta c value of 30 days and hydraulic retention time of 16 to 24 hours. So that is the extended aeration system. And the oxidation ditch, okay, or passive ditch, this is one type of activated sludge process which is working on extended aeration system, okay. Here there will not be any sludge production, okay, or the sludge production is minimal, and whatever sludge is coming, it is completely stabilized, so we can discharge them into the sludge trying bed and all, okay. So this shows the photograph of a oxidation ditch, okay. This is a type of brush aerator, okay, it is a surface aerator. So it will be aerating the system and it will be giving the horizontal velocity for the flow, okay. I will show you, this is the schematic of a oxidation ditch, okay. here we have the brush aerators, and the influent will be coming like this, and it will be going around the ditch. Okay, this is a ditch, long narrow ditch. So definitely plug flow will be, the flow regime will be plug flow, and it is going like this, and whatever the sludge is there, everything will be getting recirculated, and the treated water we can collect from here, and definitely we will be giving a secondary clarifier. So whatever the biomass coming out, it can be settled here, and entire sludge will be recirculated into the system. Okay, and the working principle of this oxidation ditch is nothing but extended aeration system, and it is a compact unit. Sedimentation, aeration and sludge stabilization are taking place in one unit. Okay, we don't have to provide a primary sedimentation tank or a sludge digester. Everything will be taking place in the same system, and it is very good for small communities. Okay, if Q is less than 3800 meter cube per day or population is less than 1000, this unit is preferred. If the Q is more, then what will happen? The area required for the system will be very high. So at that time, this oxidation ditch is not recommended. Okay, and don't get confused with oxidation ditch and oxidation pond. Okay, oxidation pond is entirely different from oxidation ditch. We will be discussing about oxidation pond later. Okay, oxidation pond is not an activated sludge process, whereas oxidation ditch is a modified version of conventional activated sludge process. And the features of this oxidation ditch, the HRT varies from 24 to 48 hours, and theta C, the biological sludge retention time is more than 30 days, and entire sludge is recycling. Okay, usually what happens, around 95% of the sludge is recycled and 5% is wastage or wasted. Okay, this will take care of the accumulation of inorganic substance in the system, and horizontal velocity of the wastewater varies from 0.3 to 0.4 meter per second. Okay, it is controlled by the brush aerators, and all the solids are in suspension. Okay, the brush aerators are placed in such a way that all the solids are in suspension, and MLSS concentration varies from 3000 to 5000 milligrams per liter. Okay, now we will see the other modification of activated sludge process, that is contact stabilization process. So in activated conventional system, we have an aeration tank and a secondary sedimentation tank, but in contact stabilization tank, we will be having a contact tank initially, then secondary sedimentation tank, then the stabilization tank. So that is why it is known as contact stabilization, and this process is used or useful for wastewater which contains lot of colloidal particles. Okay, for example, the waste is coming from the dairy industry, it will be having lot of colloidal particles. So if colloidal particles are present, it will be very difficult for treatment. The reason is, we have seen how what is the mechanism of mechanism by which the microorganisms are utilizing the organic matter. The first step is the organic matter has to go and get attached to the microbial cell, then it has to penetrate through the cell wall, then only the microorganism can metabolize it and produce carbon dioxide and water and whatever the other products. But if the particle size is very high, okay, for example colloidal particles, the particle size will be much higher compared to the cell. So those particles will not be able to penetrate through the cell. So how can the cell utilize the organic matter? It will be very difficult. So before utilizing that one, the microorganism have to hydrolyze the colloidal particle, okay, or split that one into small pieces so that it can penetrate through the cell wall. Okay, so how is it possible? Or if you want to go for this hydrolysis, and you know that in conventional activated sludge process, aeration time is only 6 to 8 hours. Okay, so this time may not be sufficient for the hydrolysis and penetration through the cell and the metabolism. So if you want to treat really the colloidal particles in a conventional activated sludge process, the time required in the aeration tank will be very high, okay, that will become uneconomical because that much time we have to aerate it and the volume of the tank will become very huge. So, to avoid that one, this modification has come up. So, that is what I have written here. Wastewater rich in colloidal organic solids besides soluble BOD, okay, this process is suitable. Example, dairy industry and meat processing industry. So, if you see the filtrate BOD in such cases, we can see this trend, okay. So, this is the filtrate BOD with respect to time. Initially, the filtrate BOD will be very high and the microorganism will be start utilizing it. So, it will be reducing. So, only soluble BOD is there, this curve will be having a trend like this, okay, like this it will be going, okay. But if colloidal particles are there, what will happen? It will be going like this, and meanwhile the microorganisms will be hydrolyzing the colloidal particles and making them in the soluble form. So, again the soluble BOD will be increasing like this, then again it will be decreasing. So, okay, this is the pattern of filtrate BOD or the soluble BOD. So, this process is known as BOD bleed back phenomena because initially the BOD is coming down, again it is shooting up and again it is coming out, okay. So, this is known as BOD bleed back phenomena. So, if the BOD profile is like this, so how the oxygen utilization or oxygen uptake rate in the system. So, initially the oxygen uptake rate will be 0, the starting, then it will be suddenly increasing, okay, because we can see that as the BOD decrease, okay, because that much of oxygen will be consumed by the microorganism. So, the oxygen uptake rate will be increasing, then as it comes down, this also will be coming down, and again here is a peak for the BOD. So, again the oxygen uptake rate will be increasing and it will be coming down. So, if you want to go for a conventional aeration tank or conventional activated sludge process, we have to provide this much of time for the complete treatment of the waste, and we will be aerating it continuously. So, here the oxygen will be utilized, and here whatever the oxygen we are supplying, it will not be utilized because the oxygen requirement is very low, and again here we are utilizing the oxygen. So, what in this process, in the contact stabilization process, what is happening is, in the first tank will be taking care of this portion, okay, and the second tank will be taking care of this portion. So, we will see in detail, okay. So, this is the profile. If the BOD is completely soluble, the filtrate BOD will be goes on decreasing. So, if you see the oxygen uptake ratio or oxygen uptake rate, initially it will be increasing, then it will be decreasing, there will not be any further increase. So, this is the schematic of a contact stabilization tank, okay. The wastewater is coming with a flow rate of Q and a BOD of S0, and this contains both colloidal and soluble matter, and this is the contact tank with a volume of Vc and biomass concentration of Sc and BOD of Sc, because here the soluble BOD is getting changing from S0 to Sc. Then this is coming, this is the secondary sedimentation tank. So, if we waste the sludge from here or here, the effluent flow rate is Q minus QW and biomass concentration is Xc and BOD is Sc. And here what we do is, a portion of the sludge will be going out and remaining will be coming to the stabilization tank, okay. Flow rate is RQ and BOD, soluble BOD is Sc and biomass concentration is Xu, okay. And this is the volume of the stabilization tank Vs, Xs and Ss, okay. Here this Xu, okay, the difference with the conventional plant is that, okay, in the contact tank we give the detention time very less, maybe 30 minutes. So, what will happen, whatever is the soluble BOD which is highly degradable, that will be getting degraded and some biomass increase will be taking place, and whatever is the colloidal particle, we give enough time here so that colloidal particles will be getting attached to the microbial cells. So, we will be having biomass which is having the colloidal particle attached to them, and that one will be coming to the secondary sedimentation tank. Here the biomass is getting settled, along with that one the colloidal particles also, but we are giving sufficient time here also, we are giving 1.5 to 2 hours in the secondary sedimentation tank. So meanwhile the microorganisms will be secreting extra cellular enzymes which can hydrolyze the colloidal particle. So along with the biomass, the colloidal particles also will be coming to the stabilization tank. By the time it will be almost hydrolyzed, or it must have become in the soluble form. So here the stabilization tank we are again aerating. So whatever is the BOD available in the soluble form along with the microorganism, okay, it will be utilized by the microorganism, and more cells will be getting generated, and only biomass will be coming to the contact tank. Okay. So we will see the volume of contact tank plus aeration tank. We will compare in contact stabilization and conventional tank. Okay. So when we talk about this one, in conventional system we need a primary settling, okay, and usually the detention time we give as 1.5 hours. So naturally the volume required is 1.5 times Q. But in contact stabilization tank, okay, we don't want to remove any suspended organic matter, because the stabilization tank and the contact tank will be taking care of that one. So flow retention is 0, volume of the tank required is 0. And aeration tank, usually a detention time of 6 to 8 hours are provided. So volume required is 6 into 1.5 Q. And here only 30 minutes is given in the contact tank. So the volume required is 0.5 into 1.5 Q. So this 1.5 Q is coming, we are assuming a recirculation of 50%. And sludge stabilization or stabilization tank is not present in conventional system, whereas in contact stabilization stabilization tank is present, and we usually give an aeration time of 6 to 8 hours. So the volume required is 6 into 0.5 Q, because we can see here, see the recirculated thing only is coming to the stabilization tank. So the flow coming is only 0.5 Q. So that's why the volume is 6 into 0.5 Q, and final settling 1.5 Q is there. So the volume required is 1.5 Q. Here also secondary sedimentation tank is there 1.5, and the volume required is 1.5 Q. So if you sum up the volume in conventional tank and contact stabilization in terms of Q, we can see that conventional aeration, conventional activated sludge process require a volume of 12 Q, whereas contact stabilization require a volume of 5.2 Q. That means the volume required in contact stabilization process is only 50% of that in conventional activated sludge process. So what is how we can design the contact tank? Contact tank design is based on the not on the BSRT, because we are not converting all the organic matter present in the system. It is based on sorption time, because whatever is the colloidal particle present in the system, we want them to get attached to the microbial cells. So the adsorption process is more important in contact tank than the biodegradation. So we have to design the system for that purpose. So we know that adsorption is a very fast process, so the time required for adsorption is very less. That's why contact tank we give a contact time of only 30 minutes. And sorption of colloidal and soluble substrate on MLSs take place, and we are assuming that though there is slight increase in the biomass concentration, because soluble BOD is present and we are giving an aeration time of 30 minutes, but we are assuming that no increase in biomass concentration take place in contact tank. And in stabilization tank, what is happening? Stabilization of colloidal and soluble BOD by microorganisms are taking place. So naturally there is an increase in biomass concentration, and stabilization tank of contact stabilization process is designed the same way as the aeration tank of conventional activated sludge process. That means the design is based on BSRT. Detention time in stabilization tank is 3 to 4 hours, or sometimes it goes up to 8 hours. Okay. Now we will come to the next process modification, that is sludge reaeration. In the earlier stages, aeration equipment was having very poor capacity. So they were not able to provide the oxygen requirement, whatever was required in the aeration tank. So, to reduce the oxygen requirement, the initial stages where the oxygen requirement is very, very high. So, what we usually was done is the secondary sedimentation tank sludge, whatever is recirculated to the aeration tank, it was aerated, so that the microorganism will be in a highly active stage, okay, and there will not be any oxygen deficiency experienced by the sludge. So, because of this one, the oxygen requirement in the inlet of the aeration tank could be considerably reduced. So, in that condition the sludge was going anaerobic. So, to make the sludge aerobic condition, the reaeration tank was provided. So, the system is something look like the contact stabilization, but the process was entirely different. Here all the biodegradation is taking place in the aeration tank, and this reaeration is just to make this system aerobic. That was the only purpose of reaeration. Here no biomass increase or degradation of organic matter was taking place. Okay. In the aeration tank all the treatment is taking place, but in contact stabilization process it is entirely different. Now we will see, okay, we have discussed about various process modifications, that we have discussed about tapered aeration system or step aeration system, we have seen extended aeration system, and we also discussed about oxidation ditch, which is working on the principle of extended aeration system, and we have discussed about contact stabilization tank, okay, which is useful for the treatment of wastewater which is having high colloidal particles. And we also seen what is this sludge reaeration system, and there is another system which is known as high rate activated sludge process. There what we do, we keep the microbial concentration low and aerate it for a short period. So, what will happen? The mu, the specific growth rate will be very, very high, or the entire system will be working in log growth phase. So, the sludge generation will be very, very high, and the treatment efficiency also will be less, because the microorganism in the log growth phase will not be secreting or producing the extracellular polymers which is responsible for the flocculation. So, in high rate activated sludge process, this flocculation of the particles will not be taking place. So much of biomass will be coming out along with the treated effluent. So, the efficiency usually is in the order of 70 to 75%. So, depending upon the purpose, okay, if you want to generate more cells, we can go for high rate activated sludge process. So, we have seen what are the different process modifications. Now, we will see what are the design considerations for activated sludge process, because this is the treatment process most commonly used for the domestic wastewater. The first one is loading criteria. So, loading criteria we can express in the terms of food is to microorganism, because the organic matter whatever is coming along with the wastewater is nothing but food for the microorganism, and the treatment is based upon the workers, that is nothing but microorganism. So, the loading criteria can be expressed in terms of food is to microorganism, okay, that is nothing but Q into S naught. This is the total food coming to the system, and total microorganism present in the system is X into VA. X is the MLSS concentration in the aeration tank, and VA is the volume of the aeration tank. Okay. So, why we are considering only this system? Because the substrate utilization occurs only in the aeration tank, and we also have seen that 1 by theta c is equal to YT Q into S naught minus XC divided by X into VA minus KD, or we can write like this: 1 by theta c is equal to YT into F is to M minus Q into SC by X into VA minus KD. Okay. Q into S naught by X into VA is F is to M, and this term will be coming, and towards the end of the time we know that this SC is very, very negligible compared to S naught. So, this term we can neglect. So, if we neglect that term, we will be getting like this: 1 by theta c is equal to YT into F is to M minus KD. So, if you design based upon the biokinetic parameters theta c, okay, it is having a definite relationship between food is to microorganism ratio. Okay. So, the loading is based upon this F is to M, okay, and we can find out the efficiency of the system. And at very high organic loading, that means very high F is to M ratio, the efficiency will be decreasing. The efficiency will be only 60 to 70%. Okay. And if you go for high F/m ratio, oxygen requirement is less. The reason is the process will be working on high rate activated sludge process. That means the entire system will be in the log growth phase. The log growth phase, oxygen requirement is less and the sludge production will be maximum. So what you need, or what is the final thing you need, depending upon that one we can change the F/m ratio. In conventional, in extended aeration system, we keep this F/m ratio very low, but in high rate activated sludge process this F/m ratio will be very high. Okay. And if F/m ratio is high, naturally oxygen requirement is less, more biomass will be generated, so nutrient requirement will be very high, and all the microorganisms will be in the log growth phase. So solid liquid separation will not be effective. The reason is flocculation will not be happening properly. So the next design criteria is excess sludge production, because whenever we talk about the activated sludge process, more and more sludge will be generated. So we have to handle the sludge. If the process is generating more sludge, okay, the post treatment requirement is more. We have to go for sludge digesters, and sludge handling itself is a problem. So how can we calculate the sludge production? We can use this formula for calculating the sludge production. So we know dx by dt, the rate of change of biomass in the system, is equal to yt, the yield coefficient, into q, ds by dt, the rate of change of substrate in the system, minus kd into x. This is the decay constant into biomass concentration. And we also know that dx by dt gross is equal to y observed into ds by dt. That means observed yield into the rate of change of substrate concentration, or y observed we can write like this, yt divided by 1 plus kd by mu. And what is the biomass produced? Okay, that is nothing but delta x is equal to y observed into delta x, delta s. So if you know the observed yield, then we can find out what is the biomass production, or biomass production we can calculate like this, delta x is equal to y observed, and delta s is nothing but q into S0 minus SC. This is the substrate utilized in the system. S0 is the initial BOD coming to the system, and SC is the BOD going out of the system. And we know what is the y observed, which we can calculate using this formula. We know yt from the biokinetic parameter estimation, and kd we know, and mu we will be knowing. So from that one we will be knowing y observed, and this is the total biomass production. But in activated sludge process, apart from the biomass, there will be other solids also. Okay, whatever is non-biodegradable, and the solids, okay, which is of nitrogenous origin. Okay, so if you want to find out what is the total sludge produced in the system, we can use this formula. Q, this is the flow rate, into y observed into S0 minus SC plus NdVSS plus F into SS. Q into y observed into S0 minus SC plus NdVSS plus FSS, where SP is the sludge produced in 1 day, and NdVSS non-biodegradable volatile suspended solids in the raw wastewater, because all the organic matter whatever is present in the system may not be biodegradable. So there will be non-biodegradable volatile organic matter present in the system, and FSS is the fixed suspended solids in the raw wastewater. So the total sludge produced will be available, because this is essential for the design of the sludge digester. And we can calculate what is the non-biodegradable MLSS in the system by using this formula. This is nothing but XNB. XNB is the non-biodegradable mixed liquid suspended solids, that is equal to theta C. This is the BSRT. BSRT by HRT into NdVSS plus FSS. If you know what is the non-biodegradable volatile suspended solids present in the system, and what is the concentration of fixed suspended solids present in the system, we can find out what is the non-biodegradable MLSS concentration in the system. Now we will see what all are the things we discussed today. we have seen that, okay, what all are the different ways we can define the activated sludge process. We have seen 3 different ways. In one system we know all the biokinetic parameters. So, using the expressions whatever we have derived for the biomass concentration in the activated sludge process and the substrate concentration coming out of the system and the recirculation ratio, we can find out what is the volume of reactor required and the biomass concentration required. The second system what we know, we assume the sludge concentration in the system and we know the SVI. So, we can find out what is the volume of the aeration tank required and what is the recirculation ratio required. And in the third case, okay, we do not know any of these things. So, what we do, we find out what is the theta c value. We assume the theta c value or the BSRT based upon the minimum theta c value. Minimum theta c value is nothing but the reciprocal of maximum specific growth rate. So, if you provide a theta c less than that one, no treatment will be taking place. Then we have also seen what all are the different modifications of activated sludge process. Those are step aeration system, contact stabilization process, extended aeration system, sludge reaeration and high rate system. And we have also discussed about what is the loading rate we can adopt. Okay, it is the food microorganism ratio. So, by varying the food microorganism ratio, what we are going to get, that also we have seen, and we also discussed what is the amount of sludge that is generated in the system, both in terms of microorganism, and we have also seen what is the non-biodegradable sludge production in the system. If we know what is the non-biodegradable organic matter concentration and the fixed suspended solid concentration. Next lecture we will discuss about the oxygen requirement and associated things.